Good evening, everybody. Pleasure to see you this evening. It is 5:48 p.m. Pacific time. We're going to start this live lecture at 6 o'clock. Hi, Lynn. Hi, Neil. Nice to see comments are coming in. We just had a little squall come through. That was fun. Sun's coming out now, though. We're no worse for wear. Hello. Let me get the laptop rolling here. So glad you're with us tonight. How's everything looking on your end? Video quality, audio quality, are we synced up? Do we have any delays or staggerings or anything like that? How's everything looking on your end? Great, great, good, 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 great, great, good, good. That all came in quickly. There's the comments, there's a little bit of a delay on my end, but maybe I'm making that up. I'm glad that everything's going well. Mechanically here. You know, you take one night off and you kind of get out of the thing. Hey, I want to do a test with you quick. Again, you early birds, we kind of practice. We got a few minutes before we start the lecture live. Where is the camera? If I look over here, I'm not looking into the camera, am I? That's way over to this. I'm looking to the right edge of the phone. I'm gonna keep my head here, but I'm gonna look over to the comments. No. Okay. So now I'm gonna come over here. Am I looking square into the camera if I look on the left edge of the phone? To the left, to the left, to the left, to the... That's it? I'm looking right now into the left margin of the camera. Is that where the frickin' lens is? More or less, yes. Okay, all right. Well, that's good to know. I think I've been looking, you know, I've done my fair share of looking into camera lenses and romper room style. Really dating myself now. But as much as I'd love to look at myself over and over and over again, I gotta train myself to look to this little... Okay. Well, that's what I learned tonight. No, there's coffee in this mug. It's about 40 degrees, man. At least the wind just died down and the rain came through quickly. I don't know, maybe I should try this board one more time. I've already drawn those lines twice. I got time, though. What are we talking about tonight? Can somebody remind me? Beach is inside. Doesn't like to be wet. Oh, flood basalts. Okay, yeah, we'll do that. I know. Water dripping off of this. Still not gonna work. Well, that was futile, but anyway. 40 degrees, breezy. This is what March should feel like around here. We've had such a mild spring. Five minutes and we're ready to go. Blood basalts, huh? Okay, let's see if I can come up with a few ideas. You may have already done this by now. Many of us kind of have been doing this every night or most nights. But for my benefit, would you mind? Where are we viewing from this evening? Bonus points for exotic locations. But we're on the honor system. You got it. You can't make it up. Mount Vernon, that's super exotic. Hello. It's rainy here, maybe rainy there too. Renton, Salt Lake City. Oh, Lord, they're coming too fast now. Got it. California, Virginia, Pennsylvania, Silicon Valley. Hello, Adrian. Hollywood, California. Yay. I'm sorry I missed a bunch of those. Port Angeles, the Olympic Peninsula, Minnesota. Is my mom here yet? Merced, Chile. Welcome. Been following this gal who's a Dutch gal who's been motorcycling across from Argentina up to Alaska, and she just got out of Bolivia yesterday. She's in Peru. Hope she's doing okay. I'm sorry, I got distracted. Ontario, Granger Clay Pits. Hello, Grandpa Carl. Exotic Spokane, Australia. This is just fun. Yeah, Itchy Boots. That's exactly. What's her name? Natalie? No. Melbourne, hello. I try not to repeat myself every night. Another Melbourne. It's so nice we're going through this and we have a way to communicate like this. It's magical, truly. Aurora, Illinois, Seattle, Washington. Okay, how are we doing on time? 2 minutes. Okay, I got to get my act together here. Well, good evening from Ellensburg, Washington, USA. Thank you for joining us. It's 6 o'clock local time, 6 p.m. Pacific. Glad that you're with us tonight. Glad that you found us. Happy that you're live joining us. And tonight we're talking about flood basalts here in the Pacific Northwest. We might comment a little bit on other flood basalt regions around the world, but I'm pretty rusty on that stuff. I know plenty about our flood basalts here. And if you're brand new to us, welcome. It's me for about 30 minutes or so, giving you content. I have loose ideas in my mind about what I want to talk about. I want to use a whiteboard and some other things. And then, since this is a live stream, we'll do some question and answer, and we'll feed off of what interests you about what I said or things that are kind of peripheral. Flood basalts here in the Pacific Northwest, collectively called the Columbia River basalts. So I think the first thing we want to do here is make sure we're not confusing tonight's topic with a few things we've done already with these live streams. This is live stream number 6. Oh yeah, the camera's here, right? How can I not look at that myself? All right, I got to train myself. I got to look at you, not me, you. All right. So, assuming you've been with us before or have watched the replays on the YouTube channel or however you've gotten to them, let's eliminate some things that are kind of familiar from even last time. Do you remember the Ellensburg blue agates? Oh, you don't? Here's one of the samples from last night. You're like, well, that's disappointing. That's a blue agate. Well, it's been cut. This is from Carl Carlson. We have a little bit of direct sunlight, so maybe I was going to say maybe the focus is better. I'm still working on the focus issue. Anyway, we talked about blue agates last time. And we were talking about basalt last time. Do you recall? We were talking about the Chianaway basalt associated with the blue agates. That is not the topic tonight. So a weird way to start. I'm actually saying, remember some stuff we talked about? It doesn't apply to tonight. It kind of does, and you'll see why in just a second. But please, the Teanaway basalt is 49 million years ago. And tonight's topic is something that's going to happen starting 16.7 million years ago. So timing-wise, we got to make sure we know what we're talking about. Do not go to the Teanaway basalt in your mind, except for a couple of things, and realize this is a much younger story tonight than the Teanaway basalt. Now, here's a map I was looking for and could not find with another one of our prior live streams, and this will get you into the right frame of mind for tonight. So here's a map, instead of one of the big posters I was showing you the other night. This is from the Ancient Rivers live stream that we did, but this is the one I really wanted to show you. I think we're in focus now, and I think we're out of my own shadow. So this, notice, has a bunch of orange on it. We're talking about this orange. And this is a snapshot from 15.8 million years ago, but the beginning of these orange lavas, these flood basalts here in the Pacific Northwest, 16.7 million. That's the date to put in our mind. But to remind you of one of the things we were doing a couple nights ago with the ancient rivers, look at the position of the Columbia River and how foreign that path of the Columbia River is compared to what we know of the Columbia River today. I was trying to describe this verbally and with the chalkboard, but I feel better now from a couple live streams ago that we actually have this Columbia River, especially downstream of Wenatchee, taking a shortcut basically to the Portland area. And that's because these flood basalts were so dramatic. There was so much Hawaiian lava flooding the Pacific Northwest, that's what we mean by flood basalts, that it pushed the Columbia River off of its former course and pushed the Columbia just for a while to this course. Then eventually the Columbia, at least downstream of Wenatchee, started to work its way back to Pasco, basically. Okay, so that is the time frame that we want, starting 16.7. We feeling like we've got a sense of that? If you're like, yeah, I've heard flood basalts, whatever. I mean, really, you're doing that? I mean, I thought you've already kind of talked about basalts. Well, I really want to ultimately get to a question of why. Why did these flood basalts happen? Is there a plate tectonic story to explain why we had these crazy lavas? And by crazy, I mean lots of lava, very fluid lava, burying and flooding much of the Pacific Northwest. We do have some ideas. It's a timing thing. It's a chemistry thing. And that's where I want to go with our discussion here. Right. That was the introduction, ladies and gentlemen. All right. We talked about a German chocolate cake, didn't we? A German chocolate cake? That's my best analogy to explain these Columbia River basalts. Let's talk about the German chocolate cake. So this is the extent of the flood basalts here in the Pacific Northwest. It's not just a couple of counties. I think I'm close enough where you can see towns. We're already down into northern Nevada. And these so everything you see in orange is a part of this kind of wrinkly, rugged, pre-existing topography before 16.7 million years ago. And all this orange lava is flooding that kind of wrinkly, rugged landscape and burying it. So if you're right off the bat looking for some new concepts, how about this one? Look in the Okanagan, look in northern Washington, in other words. Look at those details as far as the valleys, the ridges, the high points, the low points, and realize that that kind of wrinkly landscape, that rugged landscape, I mean, it's not super rugged, but it's got some, it's a mature topography. That scene, that rugged scene is underneath the orange stuff. That's a cool thought. Like many of us know the drive from Ellensburg to Spokane, it's a pretty flat drive. But it's flat because those lavas erupted onto the landscape. Think just like maple syrup, if you want to. I mentioned German chocolate cake. We're getting back to that in a second. We're looking at the top of the German chocolate cake, but I want you to have the concept. I draw it, I guess, but I don't have enough whiteboards. I got stuff pre-drawn for you. You can visualize that, can't you? So there are places like over here. Do you know these locations? So we're kind of between Lewiston, Idaho and Spokane. And there's like these islands of older topography that's there. Why didn't the flood basalts bury that? You got the question? Why didn't these wrinkly areas get covered up? And the answer is, those places were higher. Those were mountaintops. If you answered Steptoe Butte and others, that's the answer. This is Steptoe Butte and others, a well-known landmark along the Washington-Idaho border. Those are mountains that kept their chin up above this Hawaiian-like lava because they were topographically higher. But all of the lower mountaintops got buried. So that's an exciting concept to kind of think of this lost world that exists down there underneath the German chocolate cake. So why am I saying German chocolate cake? Well, if we can not look from the top down, but if we can look from a cross-sectional view, a side view, we can get back to our German chocolate cake analogy. Okay? So I've mentioned this before in earlier live streams, but let's do it again. Can I do this? We're looking down on the German chocolate cake. We're looking down on the German chocolate cake with this orange. I picked German chocolate cake because these layers are no longer orange, of course. They're brown now because they have cooled off. Here's a little piece of the German chocolate cake. It looks black, but from a distance, these layers look brown, more or less. Some of them have holes in them. Some parts in the German chocolate cake have these beautiful columns, columnar basalt. We can talk about that if you want with the live Q&A. There's places where there's pillow basalt. There you are over there, etc. So the German chocolate cake is back because I want to help you see that if we look inside of the German chocolate cake, we can realize that in places, the German chocolate cake is 3 miles thick. From the top, where we're walking around today, there's Central Washington University, there's Nicholson Pavilion, there's the Cornerstone Pizza Place, and underneath Ellensburg, underneath all those areas in orange, there is substantial layering of German chocolate cake, of the Columbia River basalts, of the flood basalts. There's 300 layers at the deepest place. How do we know that? In fact, let me give you a new map for you to show you exactly the thickness of the German chocolate cake at different locations. Hang on. I like this one. Hopefully you will too. So first of all, this is a map of the German chocolate cake. It's brown now. It's not orange anymore, so the lava has cooled off. Remember, eventually we're going to get to a discussion of why these lavas came out where they did and why they're so unusual and why there was so much lava, but we're not doing that right now. This is called an isopack map, which simply means we have lines. Almost, you see this kind of like a bullseye thing here. I'm going to get a little bit closer. And those lines, can you read it from where you are? The different lines drawn on top of the German chocolate cake are the different thicknesses of the cake. So you see in the middle of the bullseye there, that's where the German chocolate cake is 3 miles thick, and so on. Once we get to the margin, once I pull back here, so a question for you then, reading these isopacks, how thick is the German chocolate cake here in Ellensburg? I'm going to wait until I see a comment where somebody has the answer. My question is, how thick is the basaltic lava in miles below Ellensburg? How many miles? You need to find Ellensburg and then decide. That's correct. It's a half a mile. So you see this outer line has a half mile, and I'm saying beneath that half mile line, that means that if we drill down beneath that line, the German chocolate cake would only be a half a mile thick. That's still impressive. But if we go and we drill northwest of Pasco, that's the place where the German chocolate cake is the thickest. So this works. The German chocolate cake works as an analogy. It looks delicious. It tastes delicious. Again, this was a gift from a former student from the Heyday Bakery here in Ellensburg. They're closed right now. And we have layers inside. And again, 300 layers in places, especially where the thing is deep. Now, how do we know for sure those numbers I just showed you? How do we know it's 3 miles where it was, and 2 miles where it was, and 1 mile where it was, etc.? How can I show you how we figured out the thickness of these layers? Okay. Is it real information or is it just a guess? Is it indirect information? Like you look at how earthquakes pass through the German chocolate cake and you figure out the depth? I mean, we do that in other places. I'm reading your comments. I'm looking at myself because I think I'm so handsome. And then I'm also remembering, I'm training myself to look at you over there. Okay, I'm stalling for you, and seismic waves, drill cores, drilling for oil. Oh, okay. Hang on. I didn't expect the spinning, by the way. I can't get the cake off my drill, man. You can come out, Bijou. Bijou heard the drill. All right. So it is true. Shell Oil was here in the 1980s, and they drilled into the German chocolate cake because they wanted to get underneath the German chocolate cake. They wanted to know, how deep is this cake? The cake is worthless. These are the oil people talking now, the natural gas people in the 1980s here in central Washington. And they drilled and they drilled and they drilled and they drilled at a dozen locations. And they got all the way through the German chocolate cake at different locations. And they gave us a very specific set of data to show us exactly the dimensions of the cake underneath. There's so much German chocolate cake, they finally said, well, this is too much work. I think we're leaving. It doesn't pencil out for us. But they did find a decent amount of natural gas, especially beneath the German chocolate cake here in central Washington. And much of that data is still protected or not available to all of us. But some of it was made public, and so we've learned a fair amount about that. So the drill's over, the prop time's over, and now we're going to a more academic direction to try to answer some questions about why basalt, why did it erupt here, where's the volcano to make that? Some of you know the answer to that. So let's not play around, let's get right to it. Our focus point tonight is talking about these cracks. Some of you have seen this map before. These black line segments, I'll pull back for you here. These black line segments are called fissures. They're deep cracks. And the cracks, I'll zoom in now so that you can see a little bit of localities. Those are fissures that opened up and lava came up those deep cracks. And the lava came from these deep cracks. So the lava did not come from the ocean. The lava did not come from Mount Rainier. The lava did not come from any place except for these deep cracks that you can follow all the way down to the Nevada border, extreme southeastern Washington. And some of the cracks are pretty close to Ellensburg, surprisingly. So ultimately, I want to share with you what we think we know and what we don't know about these cracks. When they formed, why they formed, etc. But before we get to that, which is really the focal point of the chalkboard, which is pretty much dry by now. And by the way, again, connecting to a past live stream, do you remember when we did this and talked about the Ice Age floods? And remember the Ice Age floods dug up a bunch of bedrock and made coulees like the Grand Coulee? That's the German chocolate cake we're talking about. So that works for us tonight. So it was like two freak shows in one place. The Ice Age floods doing their weird thing and interacting with these lavas, which are also weird. Why are they weird? Why are these basalts weird? Why are they wrong for central Washington? Here's a look at common igneous rocks around the world. We got almost 400 people. No kidding? Great. Basalt is our topic tonight. It comes out of volcanoes that look like this commonly. These are called shield volcanoes. Andesite, not the topic tonight, erupts out of cone volcanoes. Rhyolite is yet another kind of lava that erupts out of supervolcanoes. This is a big caldera. I'm not going to go nuts with this board, but I do want to stress that even though we're talking about this tonight, we will talk a little bit about rhyolite for some reason once we get to the chalkboard. These numbers are percentages of silica in the magma chamber. So these are underground rooms. Think of it as plumbing system of 3 different kinds of volcanoes. And the more silica you have, the stickier the lava is, and therefore the more explosive the volcanoes are because those magmas trap gas. Tonight we're talking about 45% rock bottom silica values, pun intended. And when this lava comes out, it's as fluid as we get in nature. You can think Hawaii, you can think Iceland, you can think any oceanic thing. So, do you see the answer to my question? My question was, why is it weird to have all this basalt coming out in Washington? The answer is, basalt and gabbro, which is what happens when you solidify a magma chamber in this scene, is typically an oceanic rock. Basalt is usually found globally in the oceans. And you're like, well, no, not where I am. I live in Bend. That's not the ocean. Right, you're right. There are exceptions. But if we just come up with some basic global rules, basalt makes up the ocean floors of the world, and most of these kinds of volcanoes are found in the ocean when we melt oceanic crust. And along the coasts of continents, we find this andesite, and in the interior of continents, globally, we find rhyolites. So the global pattern is silica content differences based on global geography. There's a global pattern for these different kinds of volcanoes and these different kinds of lavas worldwide. Again, I ask my question. Why is it weird for us to have basalt in eastern Washington? Well, last time I checked, frickin' Ritzville is not in the ocean. Ellensburg, not in the ocean. Spokane, on and on and on. All these places in the Pacific Northwest are in a place where we should not have tons of basalt. I'm yelling at you now. Why is that? You're here. I shouldn't be yelling at you. I'm yelling at you because I'm excited. I'm yelling with you. What? The breeze is picked up. So here's all this orange lava, which is normally what you find in the oceans, and yet it has flooded the Pacific Northwest. Similarly, in Siberia, there were flood basalts. In the middle of Eurasia, weird lava's coming out. Similarly, in India, flood basalt, weird lava's coming out. You got my main point? We have lavas usually found in the ocean flooding the interior of the Pacific Northwest, and it's not just a dribble or two, it's the German chocolate cake, it's the 300 layers. So ultimately we want to try to explain that with the chalkboard. Hope you're enjoying this. What am I going to do next? Oh yeah. So the breeze has picked up, so this will be kind of a difficult piece of paper to show you, but I showed you this briefly last time. I found this from a field trip I did a couple of years ago. Oh God, this isn't going to work. Hang on. All right. So when the lava gets to the surface, it has so much gas content in it that it actually fire fountains. The lava actually dances when it gets to the surface, and we have miniature versions of this in Hawaii today. We have a fissure-style eruption, we have spatter falling through the sky, and there are places in eastern Washington where we can see that spatter. Even 15 million years after the fact, we can still see the spatter that landed on the ground. And we can find those cracks, those fissures, because they are what we call feeder dikes today. Feeder dikes are basically fissures that are filled with lava. Was that worth it? Maybe. All right. The last thing I want to do here with you is chalkboard stuff. And I might get carried away, but I'll try to keep it to 10 minutes. In my Geology 101 class, we spend 1 full hour going through the data, 300 layers, averaging 50 feet thick for each layer in the German chocolate cake. Thousands of quiet years between eruptions of lava. So we have sedimentary horizons and forests that we'll talk about tomorrow night with petrified wood. We go through individual features of each layer in the German chocolate cake. Columnar basalt, vesicular basalt, pillow basalt. Those are all kind of subtle things within the German chocolate cake. We have names given to different parts of the German chocolate cake. The very bottom of the German chocolate cake, we have names like the Imnaha basalts or the Steens basalts. If we're up towards the top, in other words, the youngest parts of the German chocolate cake, those are the Saddle Mountain lava flows or the Wanapum flows. But almost 3/4 of the German chocolate cake, when the system was working full bore, where we had things working full throttle and this orange stuff was just cruising, just pumping to the surface out of those fissures, those are the Grand Ronde lavas. And that's what I showed you. Can't find it. I found it. So this is Grand Ronde time, when the majority of the lavas are pumping out of those cracks. You can see the cracks now. And you can see these lavas are coming out of the Grand Ronde cracks over by Idaho, and the lavas are flowing in some cases to the Oregon coast. And the lavas are coming north of Ellensburg. And the lavas are getting up towards Omak. This is a regional story. Almost as regional as the Ice Age floods. But it's different and much older. Okay. Finally to the chalkboard. It's dried out and ready to go. So let me put these fissures on the map, just casually. You know what? No, I don't want to do that. I want to give you a key observation. You ready? Not all of these fissures are the same age. Pause for dramatic effect. Not all the fissures are the same age. The first fissures to form, in other words, the bottom layers of the German chocolate cake, formed down here. At the beginning of our flood basalt eruptions, the only cracks that existed, and therefore the only lavas to pour out and flood the landscape, were in extreme southern Oregon and down into northern Nevada. That's an important observation I'll come back to in a second. A little bit younger. In other words, the next layers, we're building our cake, right? But now this is a wrinkle. Instead of just constantly having the cracks send out all this lava all across the entire region, do you see what we're about to do? Actually, can you even see this bottom part of the map? The next cracks are here. The Grand Ronde cracks open next, between 16.5 and 16.1 million years ago. Those are the big guys. Those are the lavas that are cruising over much of the inland Pacific Northwest. The youngest cracks, and therefore the top layers in the German chocolate cake, are only up here in central Washington. So here is the point. The fissures that fed our flood basalts in the Pacific Northwest propagate through time from the south to the north. I'll say it differently. The earliest cracks formed up here, the last cracks formed up here, and there's some sort of migration of the source of these lavas going from the southeast to the northwest. Why is that? We know some things, but we also do not know other things. So I'll say it one more time. 16.7 million years ago, I'll write it down. 16.7 million years ago. If you've seen some other dates for the beginning of the flood basalts, those are slightly older dates. We have more accurate dates actually coming from horizons between the lavas, where we can get some zircons that are give us more precision. So the point is, we've got some new dates I'm still trying to get used to, by the way. But 16.7 is the new number for my head to use, the most accurate and up-to-date number for the bottom of the German chocolate cake. Why is this happening? Why is this happening starting here? What's special about northern Nevada 16.7 million years ago? Some of you know where I'm going. You've seen other lectures that we've done on YouTube, but perhaps you haven't seen any of that, so let's do it. Can we brainstorm? Is this some sort of subduction thing where the ocean floor is diving beneath Washington and making these lavas? No, because the chemistry is wrong. If we had subduction of an ocean plate beneath continent, we'd have the andesite lavas. So the subduction thing typically makes this, but we don't have andesites coming out of these cracks. We have this stuff. So I'm really saying, why did we have a heat source to make these fluid lavas, oceanic lavas? It's almost like somebody dropped an anchor in the middle of our boat, and we got water coming up through those cracks in the bottom of our boat. It is pretty watery, orange, hot magma coming up through these cracks, but starting down here and ending up here. Okay, enough stalling. Depends on who you talk to, geology-wise. But there's a consensus about many geologists, including moi, that's French, that the Yellowstone hotspot is a culprit. The Yellowstone hotspot. Now, initially that should be a surprise, because if you know anything about Yellowstone, you know that it's a volcano. And if you know more than that, you know that Yellowstone is a supervolcano. Yellowstone is a continental volcano story, and yet I'm trying to peddle the notion right now that our flood basalts are from the Yellowstone hotspot. This is like two ends of the spectrum here. Doesn't make any sense initially. But timing-wise, there's an intersection of the Yellowstone hotspot and our flood basalts. Let's draw it. Where's Yellowstone today? It's right here, right? This is the state of Wyoming. It's one of those boxy states. northwestern Wyoming. I'm going to draw a circle because that's a supervolcano caldera where Yellowstone Park is with me. Hang with me now if you don't see this. You may know that there's a mantle plume. Not all geologists agree, but let's say it. There's a mantle plume beneath Wyoming. And we've heard of the mantle, right? The mantle is what's going on inside of the earth. We don't know that much about the mantle really because it's way down deep. It's below a 60-mile thick North American plate. And we could put the word crust in here as well, but I'm choosing just to say we've got a moving tectonic plate over a mantle plume, and there's still debate. Just lost the sun, by the way. We don't really know the origin of these mantle plumes. How deep is the source of this heat? Does this all go all the way down to the core mantle boundary? Does it start within the mantle? But we know the source of these hot spots. That's what I'm talking about. A mantle plume is the same as a hot spot. We know the source of the mantle plume or the hot spot has to be deeper than the base of the North American plate, because as we move the plate, the hot spot does not move with the plate. So if the heat source was like up here, it would move with this 60-mile thick North American plate. So the model we have that most agree with, even some geophysicists, that we have a mantle plume, more or less stationary, and a moving plate. And you're like, I was with you up until this, but I've got a bad feeling in my stomach now. I don't think I understand what the hell's what's going on. Well, if our mantle plume is here today, and it is, that's why Yellowstone is a weird place. It's our oldest national park. That's the one with Old Faithful, hot water shooting out of the ground every hour. That's why there's mud pots that are boiling and like pea soup, and it smells like rotten eggs when you're in Yellowstone Park, and it's not your family. That's the gas is coming out of the, okay? Mantle plume here. But if we go back in time, that mantle plume was at different locations. Are you ahead of me now? I hope so. Where was the Yellowstone hotspot 2 million years ago? It was here. Where was the Yellowstone hotspot 6 million years ago? It was here. Northern Nevada. You've been to Denio? You're out in the middle of nowhere. Alvord Desert, you really got to work to get out there. But here's a place where the track of the Yellowstone hotspot and our German chocolate cake fissures are intersecting not only in space, but in time. We have supervolcano evidence 16.7 million years ago right here. That's why I draw a circle. So from today, progressively back to 16.7 million years ago is our Yellowstone hotspot track. You can't tell me, you cannot tell me that there's no connection between the Yellowstone hotspot and our flood basalts, because we're starting our cracks and we're starting the Yellowstone hotspot track in its well-behaved sense, the same place at the same time. Now, obviously, there's other questions that come from this. Why isn't this a bunch of supervolcano stuff? Why aren't there tons of flood basalts here? This is all just supercontinent stuff, supervolcano stuff with no flood basalts. So why do we have these two end members of the lavas exhibiting such different behaviors if they're part of the same story? That's where it gets less satisfying. And this will be an open-ended finish to our chalkboard discussion, which I'm about to wrap up. But I'm hoping that you see the logic and the reason for why we're involving Yellowstone with the origin of these cracks. We're all on pins and needles these days. We're all concerned about a lot of things. We don't need to worry about flood basalts coming down I-90 at the exit by Moses Lake. This system is done. The heat source is in Wyoming. And so we don't have to worry about flood basalts at all in our future. But back 16.7 till about 16.1 million years ago, we had a lot of orange lava flooding the Pacific Northwest. I think I want to finish there. Thank you for your attention. I'm glad you're still with us. We have a record number of viewers, 418. Oh, we had 417. Somebody just clicked off. All right, the guy's done with I don't want to stick around for the questions and answers. Well, I want to keep this rolling. I want to keep this moving. And I've got my laptop and I've got other props probably. So let's get to your questions. If you're new to us, uppercase please. I'll try to get to as many questions as I can. I'm going to scroll back to where I first see a bunch of uppercase and we'll go for it. And if I don't know the answer, I'll say, I don't know. How does massive solar flares affect our hotspots? I don't know. Hotspots are a difficult thing to explain. There are a couple of dozen hotspots worldwide. We don't know why they exist where they do. It's a major mystery. And so to involve massive solar flares, that's new to me. I don't know the connection. There's not an obvious connection to me, but since we don't have a way to even understand the basics of hotspot locations and even depth, then it's difficult for us to say much more. Mantle plumes in Siberia and India, for sure there's a hotspot that fed the Indian flood basalts. I'm less confident about a mantle plume in Siberia, but I think there must be a connection there too. Again, I'm so North American centric, and in fact just US centric, it's embarrassing. I say that all the time. I spend as much time as I can learning about local geology, and I have interest in other places, but my knowledge goes way down, so please forgive me. Could there be a hotspot supervolcano connected to other large igneous provinces? Well, that is the phrase that's used now. Large igneous provinces are these German chocolate cakes. So we have a large igneous province. And it turns out our large igneous province, which is big, our German chocolate cake, is a cupcake compared to some other flood basalt regions, other German chocolate cakes. So the question is it still there? Could there be a hotspot supervolcano connected to other? I don't know that. That's an interesting question. Are there supervolcano calderas? I don't know that. It's a good idea. I don't know that. What am I doing wrong with my scrolling? I have this problem every night. I got to go back. Okay, there we go. You like my little pinky? My dad used to drink wine with a little pinky up. Huge hands, huge farmer hands. Did the flood basalt travel down the Deschutes River in Oregon? There are flood basalts in Oregon. The Deschutes is a place where we have some flood basalts. I don't know the detail. I'm going to try not to say I don't know a bunch, but the Oregon geologists have those flood basalts mapped much better. There's picture gorge basalts. There's other specific local names that are used that confuse me because I don't know the lay of the land down there. Where will the plume be in 5 million to 10 million years? Well, we have good GPS to show us that the entire Pacific Northwest is moving southwest over the stationary hotspot at a rate of 2 inches a year. Have you ever let your fingernails grow for a year? Depending on how much milk you drink, that's probably about 2 inches of fingernail growth. By the way, all of our hairstyles are getting a little bushy, but what are we going to look like in a month without going to the barber shop? What was I saying? Yes. So there's 3 inches per year. 2 to 3 inches of movement over that stationary hotspot. So these calderas, where we've had past explosions every 600,000 years or so with the Yellowstone hotspot, will continue. And if what was your number, 5 to 10 million years? Oh, okay. Well, here's brand new back down to, let's pick 10 is Twin Falls, Idaho. So the answer is central Montana. If you live in Wisconsin, it's a shorter drive to Yellowstone Park on your family trip 10 million years from now. Are the cracks caused by the same coin purse activity you talked about last time? Yeah. Kind of and kind of not. So I was using with the Tianaway basalt, this coin purse that I got off of Amazon. Doesn't work for a damn. But I was mentioning that these cracks that are much older, remember now, and we'll come back to that on Thursday when we talk about gold, but those Tianaway feeder dikes are kind of a small version, a mini version of this huge flood basalt story, but I don't think of our squeezing, opening these cracks. Instead, this is a new idea. There are some fractures in the bedrock in much of the Pacific Northwest that has this northwest-southeast orientation that apparently goes back tens of millions of years earlier than the flood basalt. So I'm presenting the fact that it's easiest at a 100 level to just show these cracks kind of showing starting 16.7. But as you really get into the literature and talk to some of the local mappers who've done a whole career worth of working, they're kind of saying that the cracks are already kind of there tectonically from some plate motions, and then these lavas are taking advantage of those cracks. It's a kind of a, that's my best answer there. How far has this basalt mass sunk under its own weight? Did it sink in stages? No idea if it sunk in stages, but I did mention that the weight have I shown you this one tonight? So I like this one. I had these maps done locally. Jennifer Hackett, menashtashmapping.com. She's done a great job. These are custom maps from a few years ago. So here's some, maybe this brings this home a little bit more because we've got local communities. Many of you are viewing from these different communities. And so the question is, how much did the land sink? Well, let's think about it. The elevation at Pasco, which is in the middle of the German chocolate cake, is probably just, no, let's pick a number, I don't know, 200 feet above sea level, okay? And the German chocolate cake is 3 miles thick. So we can assume, I think, that Pasco, 17 million years ago, was above sea level. So the crust beneath the center of the German chocolate cake has been depressed, has sunk over because of the weight of the German chocolate cake by 3 miles. So you're probably displacing some mantle beneath that depressed crust, sunken crust. It's the opposite of isostatic rebound, where you have an ice sheet that's heavy and then you remove the ice sheet and then the land rebounds. Well, this German chocolate cake showed up, depressed the land, and this is not an ice sheet that's going to melt. It's just going to sit there. So we've had that lost, rugged world. That's how we started this, remember. We've got that lost, rugged, wrinkly world that's not only buried beneath the lava, but buried 3 miles thick. At least that works that way in my mind. Starting to get hungry. We might have to have a little German chocolate cake together to finish up. That'll be our toast tonight. How far north of Spokane did the flood basalts make it? Not far. Chewelah, approaching Chewelah. Is the East Pacific Rise part of the explanation for these lava flows? Interesting question. There's been a lot of discussion about, is it totally a hotspot story? Is it possible that the East Pacific Rise, which is a spreading center that used to exist offshore in the ocean, the East Pacific Rise has slipped beneath North America in many places, and the East Pacific Rise in any divergent plate boundary is a place where the crust is being extended and basaltic lava is coming up. So is it possible the East Pacific Rise is beneath these cracks? At least at this latitude, the answer is no. The East Pacific Rise is still offshore. It hasn't slipped beneath us yet. So if these cracks and if this flood basalt stuff was simply down 500 miles south, then it would be a decent question. Yours is a decent question, but it would be more likely. But this far north, I don't see the East Pacific Rise as being a part of the story. Let's keep it going. Oh, Eric retracted his message. So are there fissures over the hotspot instead of volcanoes? Well, the fissures are the volcanoes. If you're thinking of a volcano as a mountain, you're right. We never had a mountain. This lava is so fluid that that's why I use syrup. It just spreads laterally like syrup over the kitchen table. So if you mean mountain, you're right. We never have a mountain. But the hotspot is fueling that. We didn't really have mountains here either. This is so explosive that we just have a little hill that eventually gets blown up, and we have amazing stuff. I'm not covering much ground here. We got a lot of good questions. Why did the cracks form north of the hotspot but not south of it? Okay, these are all good. There are some fractures that have been found south into Nevada. We're away from Washington, so I know very little about it. The basin and range extension, which we did on our first live stream last week, has extended the crust, has broken the crust, has manipulated the crust so much that it's difficult to find those fissures. In other words, there's been so much recent activity in Nevada that it's difficult to reconstruct what Nevada was like during this time. So we're seeing the northern migration. That brings up, you might have a couple questions on this. If these fissures are tied to the Yellowstone hotspot being here 16.7 million years ago, why don't we have fissures getting younger and younger and even into Montana? And why don't we have flood basalts getting younger and younger and tying with this? Decent, maybe you had that question. We're getting complicated now. Right here is a major boundary between the craton of North America, which is Precambrian and very old and very thick and very stable, and everything on this side, which are exotic terrains that I'm sure we'll talk about at some point in the next couple of weeks. This is a major boundary between the old basement that's solid and the quote-unquote new basement that's not as solid. Many think this is not an accident that our fissures are forming at that boundary. And what I'm trying to say then is that we don't have a ton of fissures here because the crust is very old, it's very thick, it's very difficult to break open. Is the North American plate thinner in the area of the basalt floods? I kind of mentioned that. The thickness of North America's plate does drastically reduce once we get over here. Basically, we don't have a craton over here. We don't have this thick basement. But I think these cracks are popping up at this margin. Is the North America, how many magma plumes are there around the world? Hotspots? A couple dozen. And people have worked with those mantle plumes. There's a website if you're really interested in mantle plumes. It's called mantleplumes.org. And there's all sorts of wonderful research there. People have been studying these plumes for 50 years now. Some are found in the oceans, Hawaii. Some are found at divergent plate boundaries, Iceland or the Galapagos. Some are found in the middle of continents, Yellowstone. Nobody's figured out a pattern or an overarching system for why these hotspots exist where they do. Oh, a red question mark icon. That really stands out. That's a clever trick. Warhawk me. Is the current clockwise motion of the Pacific Northwest a result of the flood basalts? Not a result of it. We know the clockwise rotation, which we'll talk more about down the road, was going on before this story here and has been going on since that time. The clockwise rotation, as we understand it, is being driven by the two ocean plates offshore. Why didn't the land sink significantly where the fissures were located? Yeah. I guess because we need to, interesting question. Why don't we have the most land sinking here, right at the fissures? I guess because the lavas were flowing generally to the west. Did you notice on the maps? So there was kind of a paleo slope. You know, this is basically water flowing downhill. These lavas are like water. So because we're stacking up the German chocolate cake on this side of the fissures, that's where we have the most sinking. When did basalt in western Washington happen? If you're talking about the crescent formation or the crescent basalt, that's part of Silesia that we talked about a while back, and that's much older, 55 million year old basalt. If you're not talking about that, then I don't know the answer. Why do you think the fissures did not follow along with the hotspot? I just discussed that, thank you. Can you trace the hotspot out to the coast 55 million years ago? Why not? There's a few geologists, not many, that think that this hotspot track continued. In other words, this is 16.7, and we definitely do not see the calderas continue through Northern California, going back older and older. But Oregon geologists are starting to map there are scattered supervolcano calderas in Oregon that generally get older as you go towards Tillamook, Oregon, including the Crooked River caldera, if you know Smith Rock. And you're like, okay, well, so why are these here? Well, the clockwise rotation has been taking calderas, this is the idea, taking the calderas that were originally lined up by the Yellowstone hotspot and have been moved at various distances away from that original linear trend. So we perhaps do have calderas from the Yellowstone hotspot that go back earlier than 16.7, all the way out to Silesia 56 million years ago, but that's not our topic tonight. How we doing? Oh yeah, we got 5 minutes. There's tons of questions tonight. I understand why. This tectonic stuff is fun. Can you see the remnants of the fissures from the air? Nope, you really can't, Maria. Most of them were buried by younger lavas. There's one place south of Ritzville where you can see the spatter, and you might be able to see a little bit of linear trend, but the Ice Age floods came through there and ripped up the ground, so it's not obvious. So was the mantle moving? I'm weak on geophysics. I know next to nothing about the core and the mantle. There are geologists who do nothing but study the mantle and the core indirectly. There's no direct evidence. There's nobody drilling with a super... You want me to get the drill again? So I can barely say anything intelligent about the mantle. But in general, if you have a way to get material that's inside of the earth towards the surface of the earth, they're going to take advantage of that. There's less pressure up here. But that's such an embarrassingly simple question. We're going to move on. I mean, answer. We're going to move on. Not question, answer. Any chance of the old Farallon? The timing's wrong for the Farallon to be part of this story. Thank you. What's the theory about why the fissures migrated north? Yeah, that's a problem. So not all of this has been solved. I hope most of these end this way, right? So here's the question, in line with Eva's question. Why weren't the Grand Ronde lavas, in other words, when the system was pumping out these huge, thick lavas, if the first fissures were right on top of the hotspot, why weren't the biggest lavas down here? Why did we wait a couple of 100,000 years until the fissures got here to get the massive cake building chapter? Don't know. Why are these cracks working this way? Well, in general, the idea is this heat source is so big, it's more than just this little circle, that you're flexing the crust and you're kind of having this migration of volcanism in all directions away from where the hot spot is, but it doesn't really work very well. Again, I don't see how you can ignore the Yellowstone hotspot with our flood basalts, just because of the basic stuff we laid out. But there are some problems with the timing and the spacing of this stuff. Why were there fissures and not volcanoes? The lava's too fluid to build a mountain. How does Smith rock? We just did it, thank you. How old are the youngest flood basalts on Earth? Well, as far as these large igneous province worldwide, ours are the youngest. Our German chocolate cake is small compared to the other German chocolate cakes, but also the youngest. You know, there are people who fight much of this and they say, well, show me flood basalts today. I don't even think this really happened. Well, to me, that's like, well, show me the dinosaurs today. Otherwise, I don't think it really happened. I mean, we're losing an ability to think logically, number one. But, you know, we do have basalt coming out today during our lifetime, in the last 100 years, let's say. We've got video of it and everything else, but the scale is so tiny, you really can't call it flood basalts. What's the connection between supervolcanoes and fissures? I tried my best to explain that, although I'll add one thing. I guess that's what I was planning on doing here. So I'll take your question and run with it. How is it possible to have supervolcanoes and fluid lavas from the same mantle plume? And people are still working on this, but the basic idea is, let's take the Yellowstone hotspot and put it at Twin Falls, okay? Roughly 10 million years ago. So now we've got this heat source that's just heating up this plate. And the first thing generally to happen, I'm talking about supervolcano explosions along the Snake River Plain, which is kind of peripheral to what we're talking about here, but play with me anyway if you would. So the first thing to happen is the supervolcano thing. So we have this amazing explosion. It took hundreds of thousands of years to develop the pressure necessary to have the supervolcano. So we basically heated up continental crust to create this supervolcano. But after that, after the supervolcano event, if we wait many, many years, there's some mid-crustal levels where we have some mafic magma, some fluid lava, the basalt in other words. And the basalt's going to start flowing and flooding and totally burying the caldera. So these calderas, have you been to southern Idaho? Have you driven that I-86 and I-84? My in-laws are in Pocatello, so it's a long drive with kids and a little tiny Toyota Tercel. But it's flat. The Snake River Plain is flat. Those Mormon potato fields are, they're growing all that on top of the basalt, and the supervolcano calderas are underneath. So what I'm trying to say is we have bimodal volcanism, it's called. Two opposite kinds of lava coming from the same system, and I guess I'll stop there with that. It's 7 o'clock, but I'm going to continue for a few minutes. There's a lot of questions here, so if you want to hang with us, go for it. If you want to go do something else, I guess it's a free country. I guess it's a free world. World be free. Is surface lava made of melted crust or is it fresh magma? Both. Good question. Is it possible the caldera was bigger 16.7 million years ago, causing more floods in Oregon and Washington? Is it possible the caldera was bigger? Using geophysics and other things, we have a good sense of the rough scale and size of these old calderas, even though they're buried now, and they're all in the same ballpark size-wise. Were the flood basalts caused by upwelling from mantle plume, upswelling? Yeah, I don't know. Does this work? We have the hot spot underneath this area, and we're just kind of swelling the crust. We're kind of doming the crust regionally. And as we dome the crust, we crack it. What's an analogy? Like you're baking bread maybe, and the crust of the bread, as the bread in the bread pan continues to rise, we're kind of doming and cracking the crust. I got to cut myself off here at some point, but I'm having a good time. I hope you are too. I barely scrolled through any of these yet. This is a blast. Still got 400 people. What is the date range for the flood basalts? I used to have it memorized because the way I used to teach it forever, but a new paper came out 3 years ago with very new, precise dates that we're all using now. Basically 16.7 at the bottom of the cake and more or less 11 million years at the top of the cake. But damn near all the cake is there by 16.1. 16.7 to 16.1 is the best way to answer the question. Are there any known extinct hotspots, or are the one? There it goes again. We struggle with basic questions about hotspots. Why do they start? Do they start? Have they always been there? Are there any hotspots who have just gone away? We don't know. I got to figure out what I'm doing with my scrolling problem, but I lost some of those, sorry. How did the Yellowstone hotspot back 16.7 trigger all the other fissures? I've done my best to explain that. It strikes me that the craters of the moon might be the same source. There it is. Everybody wants to ask about craters of the moon. That's almost an inside joke at this point. Craters of the moon are 2,000 years old. 2,000. 2,000. Very difficult to tie it to this story. You could maybe tie the lavas at craters of the moon to a regional Yellowstone hotspot, but only that. It strikes me that is the cake representative to an old ocean floor? Basalt's on the ocean floor, but I don't see that connection otherwise. The Farallon that descended may have it? No, don't think so. Why do you think the fissures did not follow along with the hotspot as it moved northeast? Oh, good. I've hit much of this already. What fed lava? You're using two. Oh, I see. Yeah. Why do you think the fissures did not flow along? Okay, I guess I have kind of, without knowing it, hit many of your questions. Billings will be in trouble. All right, I'm going to finish with two more questions. How do the basalt floods relate to the early Cascade Formation? That's one of the two. A totally different topic, of course, are the Cascade volcanoes. And the Cascade volcanoes is the middle of this chart, which really hasn't factored into our discussion at all tonight. There's no connection. Remember, we were talking about this for sure, but also some of this. Bimodal volcanism, but here, totally different. So we should think of the Cascades as totally separate from this discussion. The Cascade volcanoes go back 40 million years ago. So we definitely have Cascades during this freak show here. Some geologists think the Cascades were quiet during this story, and that the subduction of the Farallon plate to make the Cascades was somehow impacted or affected by this Yellowstone hotspot being close by. But I don't know if I believe that, and I think there may be just as much volcanism at that time in the Cascades, but otherwise there's not much of a connection. Last question that I feel would be a good way to finish. More craters of the moon. Are you playing with me now? Evelyn, age 7, is how we'll finish. What was your favorite rock as a child and now as an adult? Well, Evelyn, I grew up in Wisconsin, and Wisconsin's a long way away from here. And the geology and the rocks are very different in Wisconsin than they are here. My favorite rock in Wisconsin when I was your age 7, was limestone. And limestone is a tan rock that forms underneath ocean water. If the ocean is very shallow, and there's sun that goes through the ocean water, and you can snorkel and do all sorts of fun stuff with your family and swim with tropical fishes. That's where limestone forms. And back in Wisconsin, 400 million years ago, you could have snorkeled at our farm in Wisconsin. And the limestone is the proof of that. I didn't know it when I was that age, but I could find fossils, coral fossils, ocean fossils in the limestone at our farm in Wisconsin. And the ocean is a long way from our farm. So that was kind of a fun thing. Limestone's no longer my favorite rock because we really don't have any limestone in where I live now in Ellensburg, Washington. And since this is a lecture tonight on basalts, my favorite rock now is basalt. Thank you for joining us tonight, everybody. So glad that you hung out with us for an hour. Hope that you enjoy looking forward to these. Let me show you the schedule for tomorrow night and Thursday night. If you want to join us again tomorrow night, we'll be talking about petrified wood, which is intimately associated with the flood basalts. We're going to be going into the cream layers, or whatever that white stuff is, to look for petrified wood tomorrow night. And then for those that love prospecting, we'll talk about gold with a special guest on Thursday night. Thank you for tuning in. Here's to you and the rest of your family and friends. See you tomorrow night. Good night, Evelyn. Love you.